Welcome back to CS201 Walkthroughs. My name is Luke Hosh, and today we're going to be talking about problem set 8. But before we do that, please don't skip. I want to talk about some other things. We have some administrative things to cover. I want to start by congratulating you. You don't have to do this PSET, I think, so you may be done with all your homeworks for this course, or maybe this is the last one you have to do. But either way, you are nearly done with Introductory Computer Science at Yale. This is no small feat. And you should give yourself a little pat on the back. Second, I want to say thank you to everyone who's watched this channel. Hopefully you found it useful. This was sort of a random idea I had with some spare time over the summer, and I really just wanted to make sure we didn't have crowded office hours and try to explain some of the concepts better than we get to in rushed office hours, or maybe if you missed class once. So thank you for watching. Thank you to those of you who commented or provided a like or subscribed even. Thank you to those of you who came up to me drunk at Harvard Yale and said thanks for making the videos. I have a mild amount of fun doing this, but mainly I'm trying to come up with things that will be helpful for the instruction here. Along those lines, I'm going to be releasing a survey, or not a survey, a kind of questionnaire, a Google form that asks you to provide feedback on these videos, whether you watched them or not. I guess if you're not watching, maybe you won't know to fill it out. But currently these don't exist in other CS courses at Yale, and I think maybe they should. I'm not sure. I would like your guys' feedback to figure out if this is something we should do. So if you want these in other courses, if you want this in CS 223 or in other CS electives, let me know in the Google form. Provide feedback on how we can make these better, and maybe they will be in those classes next semester or when you take them. That being said, let's get into some of the content of PSET 8. So this is our first time to think really about how long things take when we're doing them in Racket. So first, I think we're asked to analyze these three functions: take, drop, and length, figure out how long they kind of take to run and why they might take different amounts of time. So if we have a list, I think take says that it will go through and kind of like pick the first part of the list. Drop will drop off the first part of the list and save the rest. And length will just kind of count up the length of the list. So sort of intuitively, you might guess that this length one is not going to take as long. It doesn't have to save elements, it doesn't take any memory, and it's sort of just following through the list, right? If you remember kind of some of the obscure syntax and not syntax, but construction of Racket, lists are actually composed of cars and cooters, and a cooter is a pointer to another list or another pair of a car and a cooter, which is a pointer to a list of another car and cooter, until this is really an empty list, right? So eventually at the end, this cooter will point to something with no car, or the car will be nothing, or something of that sort of general format. The length just needs to follow these cars and count up with some sort of counter, right? So it goes 1, 2, 3, 4. Our list is of length 4. Take has to kind of remake space. So if I'm saying take the first 4 elements of this list, it has to create another list and then put those 4 elements in, 1, 2, 3, 4, which takes a little bit of space and it takes some time. Drop, on the other hand, might be a tiny bit faster because you don't have to get new space, but you do have to remove these elements from your list. You have to put it through and then stop here. So that's a little bit of sort of intuition about why these things take the amount of times that they do and why you might get those results from time calls. Time calls, in my experience, is not super precise, so don't worry about it. The point here is just to start thinking about how long things take when they run. A perhaps better example of this that's a little bit more convoluted is what you're asked to analyze later in the PSET about sorting procedures. So I think you're asked to implement isort and merge sort. And think a little bit about why they run in different amounts of time. So the procedure for isort, I'm going to give an input list of numbers, let's say like Let's make them really out of order. 8, 4, 2, 3, 1, 6. The procedure for isort is to go through and put each in its place one at a time, starting from the beginning, sort of. So I'd see 8, I'd put it in. Next I'd see 4, I'd compare it to 8 and put it before 8. I'd see 2. Oh, this is kind of convenient, is it? And it isn't it. I would see the 3, I'd have to compare it to the 2 and then compare it to the 4 and then I would put it in between them. I see the 1, I'd put that at the beginning. I see the 6, I'd put that before the 8. The key idea here is that each time you're doing this, say I have a list of length 15. So for my very last element, I'm going to have to go through as many as 14 other numbers and compare my last number to every single one of these to tell where it should go. So if I had something like in a more general version of this, if I have n numbers in my list, the max number I'd have to compare each to is n minus 1, or basically n, right? And then n comparisons, so as many as n comparisons each. So we say that this runs in big O, which means like the maximum time it'll take, in O of n squared. Okay, right, n times n numbers times n comparisons each, O of n squared. This idea of O notation is really important for computer scientists because it allows us to kind of evaluate which algorithms are better in certain scenarios. We want ones that have lower big O's, right? Ones that run in less time at their worst, okay? And MSort does that for us. I'll try to briefly explain how. It can get a little bit confusing, but I'll give you a short example. We'll say 4, 2, 3, 1. This will break up my list in half. It'll send the 4, 2 over here. It'll send the 3, 1 over here. Actually, maybe I should do a little bit of a longer example so that we kind of see it in action more. I'll do 4, 2, 6, 3, 8, 4. I'm gonna make it unique just for fun. 9, 5. Okay, so it'll break it up in the middle. We'll get 4, 2, 6, 3 on this side. Then we'll get 8, 1, 9, 5 over here. It'll break it up again. We'll get 4, 2, 6, 3, 8, 1, 9, 5. Now in each of these, it just has to do one comparison to sort because there are only 2 elements. So here it can say, is this, or I guess we could also think of it a level further down. We could say, well, here we only have 1 element. We can just put them in the right order, right? That requires exactly one comparison. I say, is 4 greater than 2? Yes, okay, so then we do 2, 4. Is the one that we end up passing back. For 6, 3, we're just going to do one comparison. We say, oh, the order for this should be 3, 6. Here the order should be 1, 8. Here the order should be 5, 9. Then we have to take these things and put them together. So I'll erase this here. I would look at 2, 4 and 3, 6. I would start at the beginning and I would say, put in the lower one. That's one comparison, it's a 2. Then I would kind of remove the 2 from this list. I would look at the 4 and I'd say, put in the lower one again. So now that's 3. Then this moves over, put in the lower one, it's a 4. And then this is the only one with any elements left. I'll put the 6 in. The same thing would happen over here. I'd get my 1, 8 and my 5, 9. I would say 1 is the lower of 1 and 5, remove the 1, 5 is now the lower, remove the 5, 8 is now the lower, and then 9 is the last one. When I'm returning them back to the top, I would again do the same procedure. I would start with my pointers here and here. I'd say 1 is the lowest, move that now. 2 is the lowest, don't worry about that anymore. 3, 4, 5, 6, 8, 9. I should have kept my diagram there, but the structure was basically I have 8 elements here, and then I have 4 in each of these, and 2 in each of their breakdowns. So when I'm dividing something by 2, the number of times I can do that is log n. So if I have n is 8, 2 to the 3, 2 to the power of 3 is 8, I can divide this list up 3 times before I get to single elements. So this is the number of kind of these layers that I'll have. And if you noticed when I was doing my algorithm, the most times that I had to compare something in each layer was 1. So like here, I just had to compare this to this. Each thing got compared once to make up this. Oh, jeez. And these each only had to be compared once to form this. And then these each, now there are 4 elements, only had to be compared once each to make this. So in each of these layers, n elements get compared once each. So, and since there are log n of these elements, and there are n elements total that could compare to each other at most log n times each, it's log n times n, or more commonly, n log n. Okay, I hope that gave you some idea about implementing these in your Racket code and why they take different amounts of time. Just to be clear, I can maybe, so this is O of n log n. This is the fastest sorting algorithm of this type. That's maybe a little bit deceiving. It has the lowest high bound for, lowest O of these sort of sorting algorithms. N squared is obviously greater than n log n if you've taken some math. Great. I didn't go over a lot of the specific problems in this, but I've been, I don't know if you noticed, sort of gradually abstracting away from specific problems and just going over concepts. And I hope that you have some fun implementing this in code. If you have trouble, please come into office hours. Email the CS201 help email, post on Piazza, comment on this video, do whatever you like. Thank you for watching all of these. Please fill out the form, and I hope to see you in future CS classes at Yale.